Hey folks, it's Dragons3 from CanSec West here. I'm going to give you a little walkthrough of what's going on with the world of browser exploitation and the Pwn2Own competition coming up and the browser awards that are available there. We're going to take a little bit of a deeper dive to talk about the kinds of hoops and hurdles that have to be jumped through by exploit writers these days and what's interesting in the world of browsers. And along the way, I hope that we'll be able to give you a little bit of better idea of what exactly all that stuff is on your computer and what are all those tasks inside your browser and what is going on. So this is kind of like a exploitation eye view of browsers. What do you have to do to get to the finish line? So inside all the browsers, whether you're using Chrome, Edge, or Safari, or Mozilla Firefox, they're all pretty much have a multitask architecture right now. They've all evolved from the single monolithic task into multiple tasks. Typically, they have a separate one for GPU processing and talking to the GPU accelerator if you have one. They usually sandbox extensions to their own processes to limit attack surfaces, and they usually keep separate renderer processes for tabs or multiple tabs in some cases, and they have other processors to be helpers for various things and control processors that deal with networking and the URLs, etc. And it gets even more complicated than that, because inside those processors are multiple threads with lots of components, like the JavaScript engine that that is the interface from the untrusted code from the server side, where the JavaScript sandbox tries to isolate it. The WebRTC connections that interface to the microphone and cameras and give you the video conferencing applications inside web browsers and that music, etc. And the complexity of all these systems, and as the browsers themselves have evolved, have made the difficulty of exploiting them much more difficult. So this year's targets for Pwn2Own, there are 4 targets: Chrome, Edge, Safari, and Firefox, and each of them has a different set of levels that you can exploit inside the browsers themselves. If you exploit the render process only, there's one prize for Chrome and Edge. And if you get through the various layers of bubble wrap and band-aids that try to keep you out of the sandbox in JavaScript, that's another prize. And that lets you have access to the operating system level of the browser. You would then have to do another backflip through hoops to get an escalation of privileges and get into the kernel if you want to control the computer outright. So that's the basic level of prizes, but the prices have been going up because there's all kinds of mitigations and basically hurdles that are being thrown up by web browser developers to stop exploitation. So it's becoming harder and harder to get into the browsers, and we'll have to see how this year's competition goes. To understand exactly what there is to exploit in the browsers, we have to go and look at the history of browsers themselves and to look at where this code and code bases that they're the exploit hunters are poring over and that the developers are all trying to secure come from. The original browsers, NCSA Mosaic and others, eventually led to Internet Explorer and Firefox, the original classic battle between those two. And there was Opera and several others, but most of those have fallen by the wayside. Chrome eventually came along the way, and all these browsers today distill to roughly 4 different browsers, but it's really only 2.5 inside, and I'll explain why 2.5 exactly a little bit later. But roughly there's 2 general architectures that these browsers all have. They either put each tab in a separate process as much as possible, like Chrome and Safari, or they put multiple tabs into worker tasks, like Firefox does, which has exactly 4 worker tasks that each handle multiple tabs. The 4 worker tasks allow you to parallelize them over multiple cores in a CPU and get you all kinds of advantages. And Firefox has been slowly increasing the number of processes and evolving to be more like Chrome. But why is it 2.5? So let's go back and let's go take a look at the evolution of Edge. Because Edge came from Internet Explorer, which was a giant monolithic C++ code, and it was eventually split up into multiple things. And these days we're trying to get rid of it, even though it's still running on an awful lot of old computers. So the new Edge was replacing the old Internet Explorer, and that was basically a ground-up rewrite of Internet Explorer. But that was recently discarded, and there's a new Edge, which is essentially Chromium. So Microsoft has adopted the Chromium source and is now beginning to add their own bits to it. They're beginning to leverage their knowledge of the Windows platform and add more security integrations. And it's going to be interesting to see if Microsoft's branch of Chromium will diverge from the main line. Because at the end, all of these eventually come from a thing in Safari called Webkit. And it's the mother of all renderers. There are really only two real rendering systems that are used in browsers, the Webkit-based ones and the ones based on the Firefox Gecko engine. And Webkit originally came from Safari and was made open source by Apple. And that led to a lot of people securing it, a lot of people using it. It's been beaten up in pwn-to-own competitions for years. But eventually it led to multiple ports of it. So WebKit and that venerable web rendering code is in all kinds of different flavors and branches of the original evolution. WebKit's the basis for all kinds of browsers. It's a basis for Chrome that so many people use it. The divergent version of Chrome for iOS, Safari, the Qt WebKit browsers that are used for the KDE browsers and so many embedded browsers, and even the Android browsers are all based on WebKit. So that means it's possible to get an exploit that works across many browsers and many platforms. It's an interesting and important bit of code that has been beaten up in pwn-to-own for many years and made quite much harder from all the exploits. It's now become much more difficult to exploit than the usual easy pickings that characterized it in its early days. So let's go talk about the next evolutionary chain of browsers, and that's the Firefox browsers, which started out as a monolithic browser and then became multi-process over time. It now has a similar structure to Chrome and is becoming more like Chrome every day. It has one main process with GPU process. It puts extensions into one separate process and then has 4 worker tabs that contain the Gecko engine. And the Gecko engine is used by other Mozilla products like Thunderbird. It's got a number of important components, most critically for this particular presentation, the SpiderMonkey engine, which is where the JavaScript runs and where the sandbox has to be put in and escaped. So that's the other evolutionary tree. Let's go and take a little bit of a deeper look at Chrome and what's going on there. This is the standard architecture diagram from the Chrome docs that tries to explain what goes on functionally at inside the Chrome architecture, where you have browser tasks and renderer tasks. The renderer tasks take care of tabs. The browser tasks take care of coordination and communication. But the source doesn't look anything like this. The bits where you're going to be looking for bugs look a little bit like this, and you can see its prominent resemblance and heritage to the WebKit browser. But Google has changed various parts inside, and there's for instance, a new Blink rendering engine. So it's evolved from the same source, similar in many ways, but also different in many ways, with different mitigations and its own different ball of wax. Inside the code itself, however, it doesn't bear the same much relationship to what's actually in the processes, in all those tasks on your computer. So here's a better description where roughly the small boxes correspond to threads inside of a process, and the colors correspond to tasks that are different, processes that are different tasks. So you have the browser tasks, Zygote tasks, renderer tasks, GPU tasks, utility tasks. Let's take a look at these, each one in turn. The browser task is where all the fun is. This is the finish line if you're going to be exploiting the browsers, because this is where all the high privilege stuff happens. This is where the networking goes, the URLs get requested, the cryptography happens, the file system access. So this is the bit you have to get into if you're going to get to the browser tasks or process holds the keys to the kingdom in terms of file, network, and cryptography access, but it's the finish line. The actual work for the exploit developers is in the next section of the code base called the zygote. And the zygote is arguably the most complicated part of the Chrome architecture. It contains lots of components, the bits of code, and it essentially spawns multiple processes as copies of itself in renderer process. The renderer itself is where the nitty-gritty of translating HTML and doing the JavaScript and rendering everything all happens for each tab or multiple tabs if Chrome is running out of room. And it's really the first place of the exploit writers have to look for code and to get through and to exploit. The renderer talks, if you have a GPU, to a graphics acceleration task, which does all the heavy lifting of the bitlets and moving bitmaps around the screen, video chunks, and does all that stuff to offload the CPU very quickly. And it's, again, only present if you have a GPU. For video, there's also another task, particularly for sound and video, the utility task that does all kinds of other little bits, like grabbing your webcam input and sending it out to Zoom, or your microphone, or playing that super annoying loud web page that didn't mute the sound on entry on your speakers. So this is the overview of the overall tasks that you have to get through, but most of the time the code you control is in JavaScript, which is wrapped by another layer of protections. And the best metaphor I have for JavaScript is it's a layer of bubble wrapped in a giant ball of duct tape and band-aids to protect the code and the other bits of the browser from that code. The Sandbox mitigations have been evolving over time, and it's been a continuous race and battle with the exploit developers coming up with evasions for the mitigations that keep pushing the bar for developing exploits higher and higher. Originally, it started out with the classic mitigations like address space randomization and heap hardening, locking down legacy interfaces, but exploit developers found ways around that, so that led to a new set of mitigations and other additions to that list. So the colors on this particular chart roughly correspond to the timeline of when the particular mitigations were added to the Java Sandbox. And as the methods of evading the sandbox became more esoteric, the countermeasures became more and more complex, and even adding code-signed cryptographic measures and lots of things that are making exploits really difficult these days. The interesting one on this list is the red one at the bottom, the shadow stack, because that was just introduced in December and was only available on the latest Microsoft hardware. So this will be the first time at Pwn2Own that particular mitigation has faced the scrutiny of security auditors. So it's going to be an interesting contest. I hope you've learned a little bit about what's here inside your browser, and we'll see you on the streams over the next few days.